Good morning. Today's chapter, we are moving into nuclear physics. So we're going to start looking at the nucleus. We have looked at atoms. We have looked at molecules. We're going to look at the nucleus. So let's go ahead and see what we can say about nuclear physics. First of all, the nucleus is made out of protons and neutrons along with the nuclear force. Specifically the nuclear strong force that holds the protons and neutrons together. So start off with looking at the masses for the protons and the neutrons. We want to get some familiarity with these particles. So the proton, I think they might have a problem with their notation here. So this is the mass of a proton, this is the mass of a neutron. I didn't notice that till just now. So I think this is supposed to be the mass of a proton. 1.6726, anyway. See how similar these are. This is in terms of kilograms, so this is in standard units. But we've got protons and neutrons that, in some sense, are the same particle. We'll see that in more detail in a couple chapters when we look at elementary particle physics. But protons and neutrons in some sense are the same particle, and the proton is the charged version and the neutron is the neutral version. And you can see that the masses are just really similar. Now, it's handy when we're talking about protons and neutrons in the nucleus to refer to neutrons and protons as nucleons. So sometimes it doesn't, we're just counting how many protons and neutrons there are combined, and for that we'll just call them nucleons. Now, the number of protons in the nucleus determines the atomic number. So it's the number of protons in the nucleus that determine which element we're looking at. So why is it the number of protons? Well, the number of protons in the nucleus will determine how many electrons get attached to that atom for a neutral atom. And so the number of protons determine the number of electrons, and the electron configurations determine the chemical properties. So yeah, the periodic table is arranged according to how many protons are in the nucleus of each one of the elements. Now the number of nucleons would be the number of protons plus the number of neutrons, and we call that the mass number, and for that we use the symbol A. I know the symbols don't make any sense here. So the A is for atomic mass number, the Z is for atomic number, and you can see the masses are almost the same, so just by counting the number of protons and neutrons gives us a good estimate as to what the mass is. Now, different what are called nuclides. So if we take a certain number of protons and a certain number of neutrons and we combine them to form a nucleus, we refer to that as a nuclide. And the way the symbol works is that the X here is the chemical symbol for the element. So that tells us which element it is. That's what would show up on the periodic table. Z is telling us the atomic number. Now this is kind of redundant. We'll look at some examples of this. And then A is the mass number. Let's go ahead and look at some examples. Here we go. So we're introducing the idea of an isotope. So let's look at this. Here's an example of using that notation. So hydrogen is the first element in the periodic table. It's the first element because in the nucleus of hydrogen there is one proton, and that one proton in the nucleus determines its chemical properties. But there are versions of hydrogen. So I could have a proton all by itself. A proton gets classified as hydrogen. You know, that's a hydrogen nucleus. Now, we could have a neutron attached to the proton. So we could have a neutron in there as well. It's still hydrogen because it's one proton. We could add another neutron. It's still hydrogen. So we need some kind of a system, a naming system to keep track of these different variations of hydrogen. And so what we do is we go, well, chemical symbol H, they're all hydrogen. And then the atomic number is 1 for each one of those, and you can see why that's redundant, right? If I know it's hydrogen, I know the atomic number is 1, and vice versa. Now the mass number is what's changing between the different isotopes. So I've got an isotope of hydrogen 1, hydrogen 2, hydrogen 3 is how we refer to that. So hydrogen 1, hydrogen 2, hydrogen 3 are isotopes of hydrogen. And that's just, additional neutrons do not change the chemical properties, so we say it's still the same element, but it does have an effect on the mass. And so hydrogen 3 is about 3 times as much mass as hydrogen 1. Now if I add an additional proton in, so now I got 2 protons, well then it's helium, regardless of how many neutrons. Now this isotope of helium has 2 protons, 2 neutrons. That would make it helium-4. So I'm guessing most of you at some point in your science classes have played around with this, and whether you have or not, make sure that you're going back and reminding yourself how this naming system works. So these are isotopes of hydrogen. This is just one isotope of helium. There are several isotopes of helium. Now here's an example of iron 56. So iron, which goes by the chemical symbol Fe, has 26 protons, so that's its atomic number. And then the most common isotope actually has 30 neutrons. So 26 protons, 30 neutrons, and so the mass is the combination. The mass number for that would be 56. And again, it's an estimate on the mass. We'll see that it's not an exact number determining the mass. What about the size of the nucleus? We've looked at this before. Back in the chapters on atoms, we saw how really, really tiny nuclei are. And so nuclei can be estimated. We can estimate the radius of a nucleus using this 1.2 10 to the minus 15 meters. Now, 10 to the minus 15 meters is what's called a femtometer. Femto is 10 to the minus 15. The atoms were in hundreds of picometers, so that's like 10,000 times bigger in diameter. And in terms of volume, that would say the volume of an atom is like 10 to the 4th cubed, 10 to the 12th. So the nucleus takes up maybe 1 trillionth of the volume of an atom, typically. And then, different nuclei take up different amounts of space, and if you have more protons and neutrons, that tends to take up more space. So we take the mass number, which tells us the number of protons and neutrons, take the cube root, and that gives us a reasonable estimate as to the radius of any nucleus. So that's an approximation we're going to use. We're going to look at some examples of calculating the sizes of nuclei, and that's the formula we will work from. Let's see here. So nuclear versus atomic densities. So compare the density of nuclear matter to the density of the stuff around us. Now the stuff around us, let's see, what's a good way to approach this? So we're going to say that there's an effective nuclear radius. So if we run experiments, if we take a beam of electrons or something, high energy electrons, and run them into the nucleus of some material, we can look at how they scatter off of the nucleus, and that gives us an idea as to how large the nuclei are. How frequently we see one of those scatters. So I'm going to write the formula as R is equal to R naught, atomic mass number to the 1/3, where the atomic, where the R naught is now 1.20 femtometers. So that's a scaling factor for the size of nuclei. Now, if we think of it in terms of volume, the volume of, well, if we imagine the nucleus to be sort of spherical. So these nucleons, the protons and the neutrons, they're going to have wave functions. They're going to have all those different shapes that we saw for the electron, all the different wave patterns representing the protons and neutrons. But to a reasonable approximation, we can say that that's going to give us something that's roughly spherical in shape. And so the volume then would be estimated as 4/3 pi to the r to the third. And if I take this formula and cube it, then the r to the third gets replaced with r naught to the third times the number of protons and neutrons. So this is just the number of protons and neutrons. And that says the volume of a nucleus can be thought of as V naught, which becomes kind of the volume of each nucleon. Each proton or neutron contributes to the volume of a nucleus, roughly 7.24 cubic femtometers. And then what we can do is we can take that number and just multiply by the number of protons and neutrons and say that combined, the entire nucleus will roughly take up that much volume. Now, let's get back to some familiar material. So nuclear material is really, really dense. When you think of an atom, 99.99% of the mass, it's in the nucleus. So almost all of the mass of the familiar stuff around us. Almost all of the mass, well, it's all in the nucleus. The electrons are bulky. So the electrons, because of their wave functions, because of their low mass, the electrons take up a lot more space in the atoms and molecules. So when we look at familiar objects around us, it's the electrons that, when you push on a solid, it's the electrons that you're pushing against. The protons and neutrons are really packed into a tiny, tiny region within that material. So let's take an example. Here's a planet, Earth. It's got a mass of 6 times 10 to the 24th kilograms. The mass of a nucleon, a proton or a neutron, 1.67 10 to the minus 27 kilograms. That says that if we take the mass of the entire planet, you go, how much of that mass is due to electrons? Well, it's not much. It's like much less than 1%. It's much less than a tenth of a percent. It's less than a tenth of a percent. So 99.9% or more of the mass of the planet is due to the mass of protons and neutrons. That means we can actually count how many nucleons Earth is made out of. So I can take the mass of the planet, divide by a typical mass of a proton or neutron, and it says, oh, Earth is made out of 3.6, 10 to the 51, that's a really big number, 10 to the 51, protons and neutrons. Now we don't know exactly how many of those are protons or how many are neutrons, but that's the total number of nucleons to 2 significant figures. That's a pretty reliable number for the number of protons and neutrons in the planet. Now what would happen if we did this? What if we took Earth as it is now and we reduced it down to the size of the protons and neutrons? We would do that by removing the electrons. If there was some way, and we'll actually see in a couple chapters in astrophysics that these reactions do occur during the formation of what's called a neutron star. But in any case, if we had somehow the Earth was to collapse down so that the electrons were gone, well, the electrons are what are taking up all this space. So if I could pack all the protons and neutrons together, we would still have 99.9% of the mass of the planet would still be there, right? And so what size would it be? And we could take that number that we've calculated of protons and neutrons and use the formula that we came up with here. I could take the number of protons and neutrons and say each proton and neutron takes up this much volume. If all it was protons and neutrons, Earth would only be a couple hundred meters in diameter. A couple hundred meters. That would be it. If again, we got rid of all the electrons that are, big and bulky, taking up all this space, and just reduced Earth down to a pile of protons and neutrons, okay, or a sphere of protons and neutrons. Anyway, we are going to be introducing some different mass units. We're going to introduce what are called atomic mass units. Now, we've been using these some, but we're going to use them a lot more in this chapter. So it works out that one atomic mass unit is 1.66, 10 to the minus 27 kilograms. Now, what we're also going to do in this chapter, quite frequently, is we're going to need a conversion of how much is the energy equivalence of one atomic mass unit. So one atomic mass unit is the energy equivalence of, now I'm going to cover up the c squared here because that often causes confusion. One atomic mass unit is the equivalent of 931.5 MeV. And so, I mean, it has it divided by c squared here, but that's confusing because we actually don't put that into our calculators. We just do the straight conversion. That much mass is equal to that much energy. Okay, and we'll see this is going to show up quite a bit. Okay, here's a nice mass table. Here are the protons, and here's the proton, here's the neutron, here's the electron. So what we see is the proton and the neutron, almost the very same mass. Look at this in terms of atomic mass units. Proton and neutron, very close to one atomic mass unit, but it's still significantly different, almost 1% different, heavier. But the electrons are just tiny, tiny masses. Now, as far as the energy equivalence, this is the mass energy of an electron. 511,000 eV, 0.511 MeV. This is the mass, or the energy equivalent of the mass of a proton, mass of a neutron. Now, what they added to the table, which maybe it's useful, maybe it's a little confusing, is they've included the hydrogen atom. Now, the hydrogen atom is, it's a proton with an electron attached. And then there's a little bit of mass shift because of the attractive force. What we're going to find out in this chapter is that nuclear forces, electromagnetic forces have a little bit of an effect on the overall mass. So when we say that, we'll look at the examples. These are coming right up. So we'll look at some examples and see. Here we go. Binding energy of a nucleus. The example we're going to look at first is a very common isotope of helium. Makes up most of the helium that we run into, that we encounter. That's helium-4. How does the mass of helium-4 compare with its constituents? Now, what are the constituents of helium-4? Well, that'd be 2 protons, 2 neutrons, and most of the time in the chapter, almost all the time, when we talk about, different isotopes of different elements, most of the time the masses include electrons being attached. So the assumption is that, yes, it's a neutral atom that we're talking about. And so I got to include the protons and the neutrons and the electrons. If I add all these masses together, in terms of atomic mass units, following the table of the masses that we saw here, the mass of all that stuff combined is 4.033 atomic mass units. Now, when we actually go in and measure the mass of helium-4, these numbers don't match up. Mass is not conserved. I think we've been talking about that ever since relativity, I guess, that in a reaction, the overall mass of the stuff going into the reaction doesn't necessarily match the mass coming out of a reaction. So if I were to create a helium nucleus by combining protons and neutrons together, that would be a nuclear reaction. And when the protons and neutrons come together, there would be a lot of energy released during that process. And because energy is being released, the mass is actually less. the mass is actually, for a helium nucleus, the mass is less than the mass of 2 protons and 2 neutrons. And you go, well, how does that work? Well, the nuclear force has the effect of negative energy. So potential energies can be thought of as literally negative, and they reduce the overall energy, and that means they reduce the overall mass. Okay, so how much mass difference is there? Well, it's measurable. It's not enormous, but when we create a helium-4 atom, we find that the helium-4 has a mass that's lower than its constituents, this missing mass, 0.030376 atomic mass units. We can use that conversion that we just talked about just a second ago. 1 atomic mass unit of mass is the equivalent of 931.5 MeV of energy. This much mass is the equivalent of this much energy by using E equals mc squared. So what we can do is carry out this calculation, and it says that what we call this is we call it the nuclear binding energy. And the energy here that we've calculated, 28.3 MeV, what that is it's the amount of energy that was released when we formed the helium-4. Now, it's probably not one step in this reaction. You know, if helium-4 is being formed through nuclear fusion reactions, for example, if we're adding protons and neutrons together to make helium-4, it's probably done in a series of steps, and we'll see that these are nuclear fusion reactions going on inside stars. This is the process that by which most stars are generating their energy. And it's a whole series of steps, but at the end of the day, this much mass has disappeared. Well, what it's done, it's been converted into this much energy. And that energy typically has been radiated away, or it shows up as kinetic energy in the products. So now it's a nuclear binding energy, and what that means is if I were now to reverse the process, if I were to start with a helium-4 nucleus and disassemble it, I'm going to take the helium-4, I'm going to take it apart back into its constituent protons and neutrons. How much energy is that going to require? That would now require 28.3 MeV of energy. I would have to have that much energy put in to disassemble the helium nucleus. And that makes it an overall binding energy for the entire nucleus. Now what we often do is we go, okay, that's the overall binding energy of the entire nucleus, just kind of averaged out. How much energy is that per nucleon? So if I think of the energy being divided up somehow evenly between all the protons and neutrons and helium, that would mean taking this total nuclear binding energy, dividing by 4, and it says that would be 7.074 MeV per nucleon. So that's a good amount of energy, you know, 7 MeV, 7 million EV per nucleon is kind of an average binding energy. That gives us an idea of how much energy would be required to just remove 1 proton or 1 neutron from this nucleus. Now, another item I want to point out in this first example we've looked at is, I know through this semester and through last semester, you know, a lot of you have wanted to keep many, many significant figures, writing out more and more significant figures, and I've always said round back to 3. This is your chapter. You get to keep 6, 7, 8, 9 significant figures in a lot of these calculations. We have to, because in order to pick up this missing mass, we need to have, we need to have 5 or 6 significant figures. It's very common in these calculations to keep 6 digits past the decimal. So yes, this is the chapter. You get to keep all those significant figures that you've wanted to be keeping during the entire 2 semesters. All right, let's do the same thing with carbon-12 very quickly. So carbon-12 has a mass of 12.0000000 atomic mass. Is that some kind of a coincidence that this one particular isotope of carbon has exactly 12 atomic mass units? And it's not a coincidence. That's the isotope we use as our definition of atomic mass units. So we actually use a very common isotope of a, quite common element to use as a reference. It turns out protons and neutrons are not useful. We wouldn't want to say a proton has a mass of 1 atomic mass unit, because once these nuclear binding energy effects get figured in, it would throw off all of our numbers. So instead, as a reference, we just use a common isotope of a common element, and we've selected carbon-12. It used to be oxygen-16, like 50 years ago or something, 60 years, and now it's switched over to carbon-12 is the reference that is used. Okay, so for carbon-12, that's exactly 12. If I take 6 protons, 6 neutrons, and 6 electrons, following all these masses that were in my table, I find out that the combined mass of all the individual constituents add up to be 12.0989. I can take that missing mass, multiply by my conversion factor into energy. Wow, that is 92.16 MeV. Now, this is 12 nucleons. The helium-4 was only 4 nucleons. So maybe it's not fair to compare carbon-12's 92 MeV with helium's 28. What we should do is divide through by the number of nucleons to give a better comparison. So when we divide through by the number of nucleons, we find out that the binding energy per nucleon for carbon-12, it is a little bit higher, but not hugely higher. So 7.68 MeV per nucleon for carbon-12. So we would say, the carbon-12 nucleus overall is a little more stable than helium. So by dividing by the nucleon number, that gives us a good way to do comparisons. Okay, so this is a lot of writing on this one. This is just reminding us that the total mass of a stable nucleus is always going to be less than the masses of the set, even for an unstable nucleus, even for a radioactive nucleus. Any nucleus that exists at all, even if it's for a short time and it undergoes radioactive decay, the mass of that nucleus is going to be less than the mass of the individual protons and neutrons that make it up. Where has the mass gone? It's been radiated away as energy, or else it's come out as kinetic energy in the products. And this is referred to as the total binding energy. So everything we were just talking about. Now what we can do is we can take that, that number, these MeV per nucleon, the binding energy per nucleon, and we can compare as we go through the periodic table. What we find is that those isotopes of hydrogen, hydrogen-2, also called deuterium, not a pretty low binding energy, but then helium-3. Helium-4, look, by the time we get to helium-4, not very far through the periodic table at all, we're already up to 7 MeV per nucleon. And look, the very most stable isotopes of all the isotopes of all the elements, and there are, it's in the thousands, there's like 100 and something elements, 118 elements, currently on the periodic table. There are thousands of isotopes that have been identified. And the most stable isotope, one of the most stable isotopes is iron-56. And look, it doesn't go up to 9. So that's something to remember in your calculations. If you're doing calculations of binding energies and you're getting binding energies per nucleon larger than 9, something went wrong. Okay. All the binding energies of all the isotopes that we look at, these are kind of exceptions here. So except for these, binding energies are going to be between 6 and 9. Okay. Now what this chart's also pointing out to us is this. Notice that as we add more and more protons, this is the number of nucleons that we're looking at as we go through the periodic table. We're adding on some protons, we're adding on some neutrons along the way. When we get to like iron, the elements in and around iron, Those have the most stable. Those are the most stable isotopes of any of the isotopes that exist in nature. And so once you get past iron, this is tin, tin 120. This is uranium 238. Notice that their binding energies have dropped down somewhat. So they're not quite as stable. So what that does is it says that, how does energy get released in a nuclear reaction? Well, if you're adding protons and neutrons together, up until iron, you're going to release energy. The binding energy is just going to get larger and larger. But once you get past iron, it actually requires energy to create these nuclei. And by starting with heavy nuclei and taking them apart, that actually releases energy. And we'll see that with nuclear fission and fusion in the next chapter. So here is iron 56 in a little bit more detail. So here's iron 56. That would be 26 protons, its element number 26, 30 neutrons, 26 electrons. Adding all those together, 56.4634, subtracting off the mass of, this is what I've looked up for iron 56 in Appendix F. So I think I've mentioned this before in Chapter 40, that in looking up isotope masses, the periodic table doesn't work. The periodic table averages over all of the isotopes for a given element. And so to get the mass of an individual isotope, which is what I need here, I've got to look in Appendix F. Appendix F is your friend. F stands for friend. And so go back there and stare at the tables back there and see how that table works. But I can look up iron 56, and that's the mass that it gives me. Now the masses that are listed there are not just the nucleus by itself, but it's the neutral atom. So they have gone ahead and attached whatever number of electrons are needed to make this neutral. And so when I'm doing these comparisons, I need to include the electron masses. Now for the iron 56, that's a lot of missing mass. When I convert to energy, oh my gosh, 492.3 MeV. But that gets divided through by 56 nucleons. And so there you go, iron 56, 8.79 MeV per nucleon. One of the very most stable isotopes of all. Here's another kind of handy table. Along the horizontal axis are proton numbers. So what you can think of is, oh, that's telling me which element I'm looking at. The elements are organized according to how many protons. And so, you know, element 1 hydrogen, element 2 helium, element 3 lithium, element 4 beryllium. And that's how many protons are in the nucleus of each of those elements. And then what these little dots represent are the stable isotopes. And what we find is, now the horizontal axis was protons, the vertical axis is neutron number. So how many neutrons typically get attached to a nucleus in order to make it stable? And it turns out that, at least initially, very similar numbers of protons and neutrons are needed to make the nucleus stable. Okay, and you can kind of think of these as different quantum states for the protons and neutrons. The protons and neutrons have spin, just like the electrons. So their quantum states and the protons and neutrons are spin up, spin down in these different quantum states. And what you tend to do, at least initially, is fill equal number of protons into the proton quantum states and as number of neutrons into the neutron quantum states. So that starts out being pretty similar. Once you get past calcium, once you get past element 20, what we find is there tend to be more neutrons. We tend to be adding neutrons at a little faster rate than protons. Now, why is it that we need this surplus of neutrons? Because if the neutrons and protons are basically the same element, and the strong force, the nuclear strong force, holds a proton and neutron together just as well as a neutron and a neutron, or a proton and a proton. They're all treated kind of equally by the nuclear force. The protons are repelling each other. So, and this is kind of one of those, oh yeah, that's right, the protons are all positive, and they're being packed really, really, really close together. And so this nuclear force has got to be really strong, because it's got to be stronger than the electromagnetic force, even at these really short distances where the positive charges are being packed closely together. And so what happens is, as we go through the periodic table to heavier and heavier elements, we start needing more and more neutrons to stabilize the nucleus. So neutrons are a little better at stabilizing the nucleus than protons are, and so we end up with these different ratios. Okay, and that's what they're talking about here. Now, as is traditional with our notes that the text, but the publishers have provided, the electric magnetic force is being referred to as the Coulomb force, and you have to be ready to hear that get used, the Coulomb force. But remember, Coulomb force is just a way of talking about the electric force, and then sometimes the magnetic effects are going to be important too. Okay. Let's talk a little bit about radioactivity. So what this is pointing out is that kind of at the end of the 1800s, researchers realized that some elements appear to be generating high energy particles. And this was the discovery of radioactivity. They found out that they started looking at all different sorts of materials to see which of these materials were producing these high energy particles, and they've divided them up. They said that one group were producing what were called alpha particles or alpha rays, one was producing beta, one was producing gamma, and now we know what they are. The alpha particles are helium nuclei, the beta particles are electrons, the gamma particles are high energy photons. Let's take a look and see. The way the researchers could distinguish these at the time, you could take these samples of materials like uranium or radium or xenon, different elements. You could take samples of these, and some of these would produce high energy particles that would travel straight through a magnetic field. Some would curve in one direction as being a positive particle, and others would curve in the opposite direction as being negative. So they realized that in some of the decays, it was a positively charged particle coming out. In some of the decays, it was negatively charged, and in other decays, it was neutral, whatever the particles were that were coming out. And now we understand these forms of radioactive decay. So what initially was labeled as alpha decay is 2 protons and 2 neutrons separating as one package away from the nucleus. So here's an example, and it's a really large example. They drew this really big so we can see it. This is radon, this is radium, and this is helium. Now radon is actually a, and I think when I said xenon before, I was thinking of radon. This is an inert gas, but it's all of its isotopes are radioactive. It's element number 88, and one particular isotope, the 226 isotope of radon. I got this backwards. This is radium, and this is radon. Let's switch that. So this is radium, element number 88, a mass of 226, and it is undergoing what we call alpha decay, and that means that 2 of the protons are going to be gone, and 2 of the neutrons. So the mass drops by 4, and the atomic number drops by 2, and now what we have left is radon 222. And we refer to this alpha particle as the equivalent. It's a helium nucleus, right? So what happens is, this is a nuclear uh, decay that takes place. And why would it be that 2 neutrons and 2 protons would come out together? And that's because 2 protons and 2 neutrons together are very stable. That's a very stable, has a lot of a high nuclear binding energy. And so typically what we don't see is we don't see individual neutrons or individual protons separating from these nuclei. Instead, we see this particular bundle of 2 protons and 2 neutrons coming out. Now this is helium, so after the radioactive decay occurs, this helium nucleus slows down. It picks up a couple of electrons that are, electrons are all over the place. And it's just a helium atom at that point. So there is this notation that the textbook goes into. For alpha decay, they say that we start with some nucleus, and it decays into another nucleus with a reduced atomic number and a reduced mass number, and what gets released is an alpha particle, which is a helium nucleus. So let's take a look at some calculations. Let's look at, here's an example of, what are we going to start with? This is uranium-232. Now that's not a common isotope of uranium. It's not one of the really common ones, but let's take a look at it. So uranium-232, here we go. So radioactivity, we're specifically looking at alpha decay. They've told us alpha, beta, and gamma consist of a helium nucleus. I should put some plus signs there. The beta is going to be electrons, and anyway, we're looking at this one right now. So let's start with the uranium-232. Now, if it undergoes alpha decay, then that means that we've got this helium nucleus that is separating from the rest of the nucleus. And what's going to be left in this case, I'm going to lose 2 protons. So that's going to take me to element 90. When I look that up on the periodic table, it tells me that element 90 is thorium. So it's going to be an isotope of thorium. The 232 is going to get reduced by 4, and that takes us to thorium-228. So Appendix F, it's your friend. So I looked up the mass of uranium-232, thorium-228, and helium-4. Maybe they gave that to us in the problem. I better go back and look. They did. Okay. They didn't give us helium, but they gave us the others. Okay, let's talk about this calculation right here. This is the mass of a neutral uranium-232 atom. This is the mass of a neutral thorium-228 atom. This is the mass of a neutral helium-4. And what happens is when we take the mass that we start with, the uranium, and subtract off the other masses, oh look, again, mass is missing. Now what we saw before when mass was missing in the nuclear binding energy, that missing mass corresponded to a certain amount of energy. In radioactive decay, that energy is the kinetic energy of the particles that come out of the decay. So if we imagine the uranium-232 to be sitting there at rest, and it suddenly undergoes radioactive decay, then the helium-4 gets shot out in one direction, and the thorium-228 heads off in the opposite direction because of momentum conservation. Now, where is the kinetic energy coming from? And the kinetic energy is coming from here. Now, this missing mass in the radioactive decay is, it gets the symbol Q. So it gets the symbol of Q, and what we can do is say that the total energy released in the decay is Q, and I can take that missing mass, and once again, I can use my 931.5 conversion. Every atomic mass, unit of mass, is going to provide 931.5 MeV of energy. So the total energy release, 5.415 MeV. Now, if the uranium starts off at rest, then the thorium and the helium are going to go in opposite directions. This isn't going to go entirely to one or the other. is there a way we could go in and determine how the energy gets divided up? Now what we know from the last several weeks of the course, I guess, is that in a reaction like this, momentum has to be conserved. That says that whatever momentum the thorium picks up, the helium has to pick up an equal amount of momentum. So the two momenta have to be equal amounts in opposite directions. So that's a constraint. And then energy is conserved. And so this energy becomes the total available energy to be shared by the two particles coming out of the reaction. So I've written this kind of suggestively. The mass we start with is m naught. M1 and M2 are the masses of the two pieces. Because what we did back in the relativity chapter, I'm not going to go back through the derivation. Again, all we're interested in is the results. If you guys want to see the derivations, go ahead and sort through that. Stop by office hours if you've got questions. But at the end of the day, what we can do is we can go use relativity to show that this is how the kinetic energies are going to get divided up. So particle 1 will acquire a certain fraction of Q, and particle 2 will require a certain fraction, and that's how it divides up. So let's go back and look at the reaction at hand. This was the reaction we were looking at. This is the Q that we've calculated. Now the Q just came by looking at the mass differences here, the missing mass. And now what I can do is these formulas that we just derived on the previous page, here they are down here. The K1 and the K2 here, those are the formulas. I just need to plug in the masses and figure out how the energy divides. So what I did is I identified M naught, M1, M2. The M1 is the thorium. And then I plugged the numbers in. Now what I did is an intermediate step here. I was curious to actually see the way that this divides up. And so I first of all calculated just the portion in the parentheses. And look, the thorium is getting, you know, like 2% of the energy that's released goes to the thorium. And that results in 0.0935 MeV. The alpha particle gets 98%. So that's what happens, and we've seen this before in other sorts of reactions, and now we're seeing it with these nuclear reactions. The lighter particle, in these decays, the lighter particles end up with more of the kinetic energy. So the nucleus, the thorium that's coming out of this, it's not so different in mass than the original uranium. The helium-4 is much, much lighter than either of these guys, and as a result, it's ending up with more than 98% of the energy that has been released. Now we can also ask this, we could ask how fast. This gives us a way to go in and practice the stuff we learned back in chapter 36 with special relativity. So we could go in and calculate gamma factors for these guys. The gamma factors weren't especially large. This was the gamma factor for the thorium. And then using formulas from special relativity, that's a pretty good speed. So the thorium is coming out at 281,000 meters per second. That's not slow. That's really fast. What about the alpha particle? Well, the gamma factor here, 1.0014, and that resulted in a speed of, wow, now that's pretty fast. That is 1.6, 10 to the 7. That's like coming out at 5% of the speed of light, 5% of c. So these alpha particles are potentially dangerous, right, if we're exposed to it. So this is one of the dangers of radioactive materials. These alpha particles have enough energy, they're moving really, really fast. If they run through materials, they break a bunch of chemical bonds before they slow down. So alpha particles come shooting through some material, break a bunch of chemical bonds, eventually slow down, and then they're just a helium atom, right? And you can use them to blow up kids' balloons at that point. But when they're going fast, they're risky. Now, something that came up, I didn't quite address this earlier. Why are we treating the alpha particle as if it has electrons attached? That's not quite right. That's not quite correct. Well, the reason that we're doing that in these kind of decays is because when we have a reaction, actually the page I was on is probably the best one to look at. What we have to look at in these radioactive decays is, well, how are the electrons involved in this? I need to make sure that I'm correctly counting electrons in these reactions. So the correct way to account for electrons is in alpha decays to make sure that the electrons you start with are accounted for in the product. So if this was neutral, I started with 92 electrons. So what I'm going to do, just to simplify things, is assign 90 of those electrons to the thorium and 2 of those electrons to the helium nucleus for simplicity. Now what that means is that those masses are off. Well, the masses themselves are, the Q value is still reliable. So we've counted the electrons correctly. The Q values are still reliable. But when we start calculating these numbers, they're not quite. What happens in a decay like this is some of the electrons get left behind. You know, the alpha particle comes shooting out of there at 5% of the speed of light. The electrons are going to get left behind. And so the electrons aren't moving away with the helium nucleus. So it's a bit of an approximation that we're using with the numbers we've come up with. But it's going to work well for us. So it's going to give us a reasonably accurate measure of how much energy or how fast those alpha particles are coming up. It looks like we're about due for a break, so I'm going to go ahead and I think I'm going to stop there. And we'll take a break for 10 minutes and we'll come back. Any questions? Stop by.